So, hello everyone. This is lecture 7 for the special theory of relativity (STR). In the last lecture, we studied the the Lagrange invariance of this function. This is invariant, okay? So, we proved this in the last lecture. In today's lecture, we're gonna see some questions which are asked in the previous years related to the Doppler effect. We already studied the theory part of the Doppler effect. Now we see that which type of questions are asking the examiner. So let's see. This is first. A sodium source emits light at lambda equal to 589 nanometer, which appears to an observer as a copper green line of 522 nanometer. Who was moving at? So we need to find the speed of the observer. So from this expression, we can see that wavelength is decreasing. Wavelength is decreasing, then definitely the source will be, observer will be moving towards source emits light and appears to observer as a was moving. Okay, speed of observer. So observer will be moving towards the source because wavelength is decreasing, then frequency will be increasing, and frequency always increased when they are coming nearby. So observer will be definitely going towards the source. So we know for that formula lambda and lambda naught how they are related for the observer moving towards the source. Then lambda will be lambda naught root c minus v by c plus v, where v is the speed of the observer moving. Okay, so we'll just put the value here, and we can find the from here the speed. V will be 0.12 c. It is easy, direct formula base. Now there is second question. A light source moves with constant speed along a line relative to an observer standing in its path. The observer measures the wavelength of the light to be 365 nanometer as the source approaches her and 1096 nanometer as it moves away from her. So situation is like there is this, what was this? Moves with constant speed related to an observer. So there is this observer and light source is moving this side, and when it is moving towards the observer, then the observer measure the wavelength of the light to be 365 nanometer, and when it passes through the observer, then it is moving away from the observer, then it measures the 1096 nanometer. Okay, so what we need to find, we need to find the wavelength of light in rest frame of its source is about. So in the rest frame we always measure the real value, so we have to find the lambda naught. So we know from this expression we already studied the lambda equal to lambda naught root c minus v divided by c plus v. Okay, from here you can see that for when the source is moving towards the observer, then this formula will be valid, and when it is moving away, then these will be just swapped, and we will get this formula. Okay, now from here also you can find the values, just like let's write it lambda 1, it is lambda 2. Now from here you can find the value of c minus v upon c plus v in terms of lambda 2 and lambda naught. That will become as lambda naught square equal to lambda 1 lambda 2. So lambda naught will be root lambda 1 by lambda 1 lambda 2. So that's how you can find the original wavelength. Now there is this next question. A source of light S and detector D are approaching the observer O from opposite direction with speed u relative to observer. If S is emitting light with frequency mu in its rest frame in the direction of D. If S is emitting light with frequency mu in its direction frame in the direction of D, the frequency observed by the capital D is. So there is this our observer, okay, and this source is moving this side towards the observer, and our detector is moving towards the observer with speed u. So if we take this direction as u, then it will be minus u speed. So what we need to find is, if s emits a radiation with frequency mu, so that will be the real frequency, the original in the frame of s. We need to find this frequency observed by the capital D. So what will be the frequency observed by this detector? So given as speed of u s with respect to observer, and speed of d with respect to observer is given. We need to find the speed of s with respect to d. That will be give us the this expression. Then we can use this expression now, because we need to find, what we need to find is a speed of source with respect to d. Then it will be stationary, and this will be moving with relative to this, and that speed will give us the expression for the apparent frequency or apparent wavelength, anything. So we need to find the VSD. So he will use the formula, we already studied about it. Vs with respect to O is given is u, Vd with respect to O is given is that is minus u. So Vsd will be the third body, Vso minus Vdo divided by 1 minus Vso Vdo divided by c square. So just put the values and we will get this expression. Now just to put VSD inside the formula. If it is moving towards this detector, then it will be plus upside, and in the denominator it will be negative. So the apparent frequency will be the real frequency root c plus v divided by c minus v. Here VSD will be put. Then you will get this answer after solving this. Okay, that's easy. There's one more question. Consider a radioactive nucleus that is traveling at a speed of c by 2 with respect to lab frame. Okay, it emits gamma rays of frequency mu naught in its rest frame. There is a stationary detector which is not on the path of the nucleus in the lab. If a gamma ray photon is emitted when nucleus is closest to the detector, its observed frequency at the detector is. So it is given that a nucleus, radioactive nucleus, that is this nucleus is moving with speed c by 2 in this direction, and that is not in the path of the detector or the observer is here, and it is at the earth frame. So it is moving in some direction, it is not fixed. So it is saying that it is emitting photons. So it emits the photon when it is closest to the observer. So it will be closest only when it is, this path is perpendicular to this. So here it emits a photon with frequency mu naught. We need to find the observed frequency by this observer. So we know the general formula for any theta, that was this mu naught 1 minus v square by c square 1 minus v by c cos theta. Here theta is the angle between the line of the source and the detector. Okay, so here theta will be 90 for the closest, it will be 90 for the closest approach. And from this formula, well, it was written here. So cos 90 will give it 0. So we'll get mu equal to mu naught 1 minus c square by 4c square. Here v equal to given c by 2. So we can just put it here, substitute. You will get mu naught root 3 by 2. So this will be the apparent frequency. This will be the apparent frequency. Now there is one more question. A monochromatic source emitting radiation with a certain frequency moves with a velocity v away from a stationary observer A. It is moving towards another observer B, also at rest. Okay, along a line joining the two, the frequency of the radiations recorded by A and B are mu A and mu B respectively. If the ratio is VB mu B by mu A is equal to 7, then the value of mu by C is, so that is not mu, that is V by C actually. This is velocity v. So a monochromatic source emitting radiation with a certain frequency moves with velocity v away from a stationary observer A. So here is A, here is another observer B. So it is moving away from the observer A and moving towards another observer B. Okay, also at rest, both A and B are rest along a line joining the two. The frequency of the radiations recorded by A and B are this. So apparent frequency with respect to A will be C minus V, C plus V, because it is moving away from A. And for VB, that will be plus, so upside, and negative in the denominator. So the apparent frequency will be mu naught this. So we know this ratio VB by VA, so just divided, and then we can just substitute this 7 and find the value of V by C, just taking C common. Then that will give 1 minus V by C, or 1 plus C by V by C. So that's how you can calculate V by C. It will came out to be 3 by 4. Now one more question. Find the wavelength shift, if any, in the Doppler effect for the sodium D2 line 5890 angstrom emitted from a source moving on a circle with constant speed 0.1 c measured by an observer fixed at the center of the circle. So we need to find, just situation is like that. There is this, our source is moving in the circle and observer is at the center. Okay, and it is asked that will there be any wavelength shift in this given wavelength observed by the observer. So apparent wavelength we have to find, and we need to give its expression that it will be change or not, and if it will change, then how much it will change. If this speed is 0.1 c, the speed at which it is moving around the observer. So from the formula we know that when it is moving in the circles, it will always make the 90-degree angle with this line. So it will always be 90-degree, so we will put 90 here. So it will give us formula mu equal to mu naught 1 minus v square by c square. This formula will came out. From here we can find for the lambda, c equal to nu lambda, so nu equal to c by lambda. So this will be this lambda equal to lambda naught this. From here just to put we frame this, and it can be solved by the binomial expression. For the higher terms will be neglected, so initial terms will be these 1 plus v square by 2c square. And from here just put v equal to 0.1 c and find the lambda. Lambda naught is given, lambda naught is 5890 angstrom. So there will be this shift, you can check it out. This lambda naught plus lambda naught v square by 2c square, then lambda minus lambda naught will be written as delta lambda, that will be equal to lambda naught v square by 2c square. So that value will give you the shift in the wavelength. So there is this one more question that will be last for the Doppler. So a distinct source of light emitting radiation of frequency omega moves with a velocity 4c by 5 in a certain direction with respect to the receiver. Okay, so a source is moving which is emitting radiation, and that source is moving at 4c by 5 speed, and its frequency is omega. That is the real frequency, definitely, in a certain direction with respect to the receiver. So we assume this is theta angle it is making in a certain direction. It is given that the uppercut of frequency of the receivers is 3 omega by 2. So for the receiver the uppercut is 3 omega by 2. So what is the meaning of this uppercut? Meaning of uppercut is that the frequency more than this value 3 omega by 2 will not be observed by this receiver. This is limit for the receiver, that this is the uppermost limit, that more than this frequency can't be received, or it can't analyze this frequency. So it will be the maximum frequency it can analyze. If theta is the angle between line joining the source and the receiver and the path of the source, so this line and this line, the path of the source, then theta should be at least. So we need to find the minimum value of theta for which it can observe. So from formula we know that mu equal to mu naught this. So for the maximum frequency means it should be maximum. This how will you change theta so that it comes out to be maximum? For that this downward side should be minimum. So we will increase theta. If we increase theta, then this value will decrease, and it will give us, it will increase and overall value will decrease. If theta decrease, if theta is 0, then it will give maximum value, and this difference will be minimum, and it will give the maximum value of this. So for the minimum theta we get maximum mu. So this is inversely proportional. The theta will be less, mu will be larger. Okay. So if this value of if maximum value of mu is fixed, then there will be a minimum value of theta will be fixed, below which it will be more than 3 omega by 2. So if we fix 3 omega by 2 here, then we can find the minimum value of theta. Just put 3 omega by 2 here, and mu naught equal to omega, then that will cancel out, and v is given, that is 4 by 5c. From here you can find that cos theta will be 3 by 4. So theta is equal to this. So theta, this is the minimum value. Just think, this is the minimum value. If theta is less than this, then you know for the cosine that minimum value of theta will give you maximum values. So theta, if theta will be less than this, it will give you more value of cos theta, and then this distance will be smaller, and this overall value will be a larger. So it will increase more than 3 omega by 2, and it can't be received by the receiver. That's why we are finding the least value for theta, for which this receiver can observe the frequency. So that will be for the 3 omega by 2. So I hope it is clear. Now let's start a new topic, that is rotational matrix for the rotation of axis. So today we just gonna discuss some basics about the rotational matrix. Basically it is a building structure for the Minkowski's space, that is 4-dimensional space where one dimension is for the time. We're gonna study in detail about it. Before that, just you have to understand this thing, a basic understanding of rotation and the rotation frames. So just we take here that there is this one frame. Just consider this one frame, that is S frame, and we take a particle here, and its coordinates are x1 x4. So here we take it x4. We'll discuss about it later why we are taking x4. Just consider it. We take its coordinate as x1 x4, and this whole angle is phi. This whole angle is phi. Now we rotated this frame by theta angle. Now this axis will be here, and this angle will be phi minus theta. This angle will be phi minus theta. So before that rotation in the S frame, we can find the coordinates for P, x1 x4. So x1 will be, if it is S, then it will be S cos phi, and x4 will be S sin phi. Okay, because this whole angle is phi. Now in this rotated frame, we can also find the coordinates for x1 prime, x4 prime. X1 prime will be S cos phi minus theta, and this will be S sin phi minus theta. Sin phi minus theta. So if we just expand this, S cos phi minus theta, so x1 prime will be S, this is cos x minus y, cos x cos y, plus sin x sin y. This will give us this, and from here we can see that S cos phi equal to x1. This will give us x1 cos theta. S sin phi is x4 from above, so it will give us x4 sin theta. Same x4 prime can be expanded along sin x minus y, that is sin x cos y minus cos x sin y. So it will give us sin, this is x4 cos theta, and this is x1 sin theta. So we just transformed the x1 x4 in the prime state in order in the rotational matrix. So how we can represent this in the form of matrix? So if we need to find the x1 x4, we can write it like x1 prime x4 prime, then cos theta cos theta minus sin theta. Sorry, x1 x4, and x1 is here, so that will be come this side. This is the rearranged form of x4 prime. Now it is of x1, it is of x1, it is x4, it is x4. So it can be written as cos theta sin theta minus sin theta cos theta, and x1 x4. So if you multiply these matrix, it will give you these equations and this. So we can write these equations in the form of this. So you can see here that this is nothing but the transformation of coordinates in from one frame to another. Means in this that S prime frame, we can find the x1 x4 prime in the form of x1 x4. Just if you know x1 x4, you can find the x1 prime, x4 prime, and theta if you know. So this matrix is called the rotational matrix. This is called the rotational matrix, and using this you can just transform the coordinates. So just like we can transform these coordinates into this, we also can find the initial coordinates in with the help of these. So how can we find them? So just to reverse, it is given, we already found that the x1 prime is this, okay, and s4 prime is this. So and we know that s1 equal to s cos phi. So how it can be written? It can be written as s cos phi minus theta plus theta. We can write it like that. Theta will cancel out, it will give us phi. So open it, this formula, cos x plus y, that will give us cos x cos y plus minus sin x sin y. Okay, so s cos phi minus theta, cos theta minus sin this. Now from here we know that at s cos phi minus theta equal to x1 prime, this will give us x1 prime, and this will give us x4 prime. Same we will expand for x4 equal to s sin phi, then we will write it s sin phi minus theta plus theta, just like that. And again expanding sin x plus y, sin x cos y plus cos x sin y will give us this. This is nothing but x4 prime, this is nothing but x1 prime. Now we again get an equation x4 equal to this in the terms of x1 prime, x4 prime, and we get an equation for x1 in terms of x1 prime, x4 prime. So it again can be written as in the form of matrix, but the only difference is now x1 x4 are the initial coordinates can be found with the help of x1 prime, x1 prime. These sin theta, cos theta are in the downside. From the first equation, cos theta minus sin theta, x1 x4 can be written as x1 prime, x4 prime. You will multiply them, you will get these equations again. So that's how we can write these equations in the form of these matrix. And this matrix is called the rotational matrix. Now if the frame is rotated, and you know the coordinates now in the rotated frame, with the help of this you can find the original coordinates before rotation. That's why it is called the rotational matrix, and it helps in the transformation of coordinates. So we just understand the transformations in the rotational matrix, okay, and now we're gonna use this in a very wide concept of the Minkowski space, that is four-dimensional space, in the coming lectures. Okay, so just develop the basic understanding. See these equations again if you didn't understand, or go through the back lectures. Okay, from the tomorrow or the next lecture we will start the space time that is given in the Minkowski space, where time is the fourth dimension, and that will be our last, not the last lecture, but the topic will be last, and the 1-2 lecture this all special theory of relativity will be ended. Okay, and in the last lecture we'll discuss some questions. So just revise whatever you already studied and just solve the questions. Okay, thank you.